Oh, hello, very good evening to all of you. So, today I am going to give a lecture on the chapter of tract and combined stresses. So, this is basic. So far, we have discussed only the tract stresses and bending stresses. What happens when both the stresses act together? So, this is a very important chapter, and its application will be used subsequently also in pre-stressed concrete and in RCC, steel design, and everywhere we have to be aware of the effect of how to calculate the tract and bending stresses when both act together. So this is a very important chapter, and let's concentrate on that and let's start. First of all, tract stress in a compression member. What is the tract stress? As we have discussed, any structural member loaded actually in compression is called a compression member. It may be column, stanchion, post, strut, or boom. So these are the types of 5 types of compression member. Suppose I have a compression member like this, and I have applied a load P. So due to compression, it will deform like this. So as I increase the load, it will further deform like this, and finally it will fail. So that will call as a compressive strength. So it may fail by crushing and compression. So this is one column. What happens when this is a kind of short column? When we have a long column, like this, so what happens during this compressive load? It has a tendency to deform like this. So there will be some buckling here. The long column or slender column have a tendency to fail by buckling. So that we will discuss subsequent lectures. So today I am discussing only my tract and bending stresses in short column only. So in brief, these are the types of compressive members. Column as used in building to carry load of beam, slab. Stanchions like steel columns made of rolled steel sections, frequently used in the building, and a post used for columns. Strut in trusses, in roof trusses, it may either be vertical or inclined, and boom also in cranes. This is a principal compression member in crane. So during lifting, moving, or putting the load, we used this boom in application during crane operations. So this is my column. What happens when I applied a load here in both the ends? So there will be compressive stresses. Suppose I have taken as section Mn, and I cut this section in two parts. So what will be my stress distribution? My stress distribution will be like this. So this is a P compressive force. So for the equilibrium of this, compressive stresses will be developed here, and that will act on the whole area, this whole area. Similarly here, so the stress here is equal to resistance upon area or load upon area. So this is the compressive stress is developed in columns. Short column is that fell by compression, that the average compressive stress is equal to load upon area. Long column, a compressive member which is so slender, which is so long to its length, that under gradually increasing load it fell by buckling at loads considerably less than those required to cause failure by crushing. So due to its slenderness having more length, it will fail at a lesser load as compared to crushing. So I am not going to discuss long columns. I will discuss it in my subsequent lectures. My today's lecture is only for combined direct and bending stresses. So this is a simply supported beam. So vertical load, say W1, W2 and W per unit length, they are acting on a beam. And in addition to this transverse load, there is an axial load also at both the ends. So this axial load, due to this axial load, it is passing through the centroidal axis here. So this, as a result of this force, there will be compressive stresses at each sections, and that, suppose the load is P and my section of the cross section of the beam is like this. This is BD. So this load will act on this area. So as a result of this, my direct stress is PO. Suppose this is the original direct stresses, that will be load upon area. So that will be of compressive in nature and will act throughout the length of the beam. So these compressive stresses will be developed at each sections of the beam. So under this load, my beam will behave like this. I'm only this will be the effect of this compressive load. So this is my direct stress. This is my direct stress. We call it direct stresses. Direct stress means stress that has been caused because of the direct load that acts on the centroidal axis of the beam. But in addition to this, due to this transverse load, so there will be, it will deflect like this, and bending stresses will be developed also on the beam. So bending stresses will be like this. So here compressive stresses on the top, and in the bottom tensile stresses will be developed. And my stress diagram, stress diagram will be like this. Suppose this is my neutral axis. So on the top fiber there will be compressive, and on the bottom there will be tensile stresses, here compressive stresses. So due to this loading, it will, so this is my bending stresses. Bending stresses. So if I want to know my stress on the top fiber here, means at here, so this is the cross section of the beam, this is B, this is D. So on the top fiber my stress will be, this is my bending stresses, that will be equal to moment at any section, suppose we are taking moment here, so m divided by section modulus. So m upon z will give the direct bending stresses. It will be plus and minus. Plus will be on the top. In compressive it will be m upon z. In bottom it will be minus m upon z. Suppose I want to know my final stresses here. So this will be because of this direct stresses plus my bending stresses. So my final stress in the top fiber here will be because of this. This will be compressive. On the bottom here it will be my direct stress will be compressive throughout, so it will remain positive. But in the bottom fiber my bending stress will be negative. So my stress at any layer, this will be the algebraic sum of corresponding direct stresses and bending stresses. This direct stress remain constant throughout, there will be no effect. So its effect will be like this. So due to that stresses, my stress diagram will be like this. This load P upon A, this is my direct stress. P upon A, it will be compressive throughout. And my bending stresses will be like this. There will be compressive force on the top fiber, and this is my PB. It will be compressive. Here it will be tensile. So PB tensile and PB compressive. So my final stress diagram will be like this. So on the top it will be direct stress plus bending stresses, and in the bottom it will be, since it is positive and it is negative, it will be PO minus PBT, this tensile, this plus this. So this will be like this. Suppose if my tensile stress is this amount is more than this, then it may be negative here also. In this case it will become like, when my bending stress is more than compressive, it will be like this. So the algebraic sum of the direct and compressive stresses, direct and bending stresses, will be my total stresses. So combined direct and bending stresses occurs in a structural member which is simultaneously subjected to direct stresses as well as bending stresses. A compression member may be subjected to axial load which may not pass through the geometrical axis. Suppose this is my compression member, and my load A, this is the centroidal axis of this vertical member. So here my load, this W is not passing through this centroidal axis, it is acting here. So there is some amount of eccentricity. Eccentricity is the distance between the line where the load is acting and the centroidal axis of the member. So this is E. So because of this eccentricity, the moment will be created, and that will be load into this distance. So W into E, this moment, and this will be this will be like this. So this moment will be created. So if I consider both the effect together, then it will be like this. My W load, the effect because of this will be, I will place this load here on the central axis and also consider the effect of this couple. So this will be like this, and same load will be placed here, and if this is acting like this, so it will be like hogging type of movement. If I see vertically, so it will deflect like this, it will behave like this. So there will be a, here it will be compressive stress on the bottom fiber and tensile stress here. So combined direct and bending stresses occurs in structural member which is simultaneously subjected to direct stresses as well bending stresses, such as in figure. A compression member may be subjected to axial load which may not pass through its geometrical axis, causing bending as well as direct stresses. So here direct stresses is also because of this W, that will be load upon area, and due to this moment also, which is this WE. So this is also creating bending stresses. So due to bending, longitudinal stresses either tensile or compressive are set up in the cross section of the member subjected to bending. So here tensile stresses are developing on the top fiber here, and compressive stresses will be developed on the bottom fiber here. So resulting stresses will be the algebraic sum of the direct and bending stresses. So this stress will be because of the effect of this direct stress plus bending stresses, as I explained here. So direct stress will be W upon area. This is throughout compressive, plus minus bending stresses, that will be this moment upon section modulus. So on this fiber it will be tensile, so tensile will be considered minus, so it will be WE upon Z, and on this fiber it will be direct stress plus bending stresses due to compressive. We considered compressive stress as positive and tensile stresses as negative sign. So this is eccentric loading. When the load does not pass through the centroidal axis and have some distance E from the longitudinal centroidal axis, then the direct and bending stresses both will be developed. That's what I have explained here. Here the load is not passing through the centroidal axis, it is acting somewhere here. So there is some eccentricity. So that amount is called eccentricity, and as a result of the eccentricity, moment is there, and it's create longitudinal bending stresses. So that will be tensile and compressive in nature. So this is how it acts. So the load is acting here. So this is the central axis. So my load is not passing through the central axis, it is passing on this line. So the distance from the line of action of the load and this centroidal axis, this distance is called small e, means eccentricity. So suppose if I apply a equal and opposite amount of load here, this P, that this is equal and opposite amount of load here, then what happened? Because of this load and this load, there will be a movement. So this is because of this lever arm. So this will create a couple. So it will create moment, and because of this and this, there is a couple and this load. So I can place it like this. So there is a couple which amount is P into E and this direct load itself. So what I want to say that in this case you place this load exactly from this point to this point here, and along with this there will be a moment. In nature will be like this in the direction of the force. So the load is acting like this and this is the distance, so moment will be like this. So this is my moment. If I consider this section Mn, so it will be, there will be direct stresses because of this load. So that direct stresses is equal to load upon area. So this stress is because of this vertical load. And what about this moment which is PE? So because of this there will be a bending stresses, and bending stresses will be like this. So if I consider the effect of this, due to this direct stresses, my stress will be throughout compressive. This is positive. So this is a direct stresses which will be equal to P upon A. And due to this moment, there will be a bending stresses. So due to this moment, it will deflect like this. So there will be a tensile stresses here. It will be tensile, and on this face there will be a compressive stresses will be developed. So due to this moment, so effect is like this. So it will deflect in this way, it will bend in this way. So tensile stresses will be here on this face, and so it is compressive stress here and it is tensile here. So on this fiber there will be a compressive stress. Suppose if I plot this, so my stress diagram will be like this. This is my stress diagram. So compressive stress is here and tensile stresses will be here. So this my compressive stress is bending compression, it is bending tension. So this will be my stress diagram here because of this moment. So it will be compressive here and tensile here. So along this line, if I draw this diagram, it will be like this. And because of this direct load, my stress diagram will be like this. It will be throughout compressive, and that is equal to P upon A. And what will be the effect of this combined direct and bending stresses? So this will be equal to this direct load, direct stress plus bending stresses. So direct stress is equal to this load upon area, and bending stresses will be moment M upon Z. M upon Z is equal to bending stresses. So M my moment is equal to, so it is equal to P upon A plus my moment because of this is P into E. So this is moment is PE so my final stress will be that stress is, that is P upon A plus minus M upon Z. My value of M is this PE upon Z, and Z will be along this axis. because this bending is basically occurring on this axis, about this axis. My bending is this bending is, so this bending is along this axis. Along this axis, I have to take the moment of inertia and section modulus. So this, suppose this is my x-axis, so my z will be about this axis. So this will give the final resultant stress. So it will be, since it is compressive, it is also compressive, so both are compressive, so it will be like this. And on this end there is a tensile stresses, it is compressive here, so due to tensile it will be that stress minus this P upon Z axis. So my compressive stress amount will be decreased. So this is my, suppose this is my that stress, and this is my, these are my tensile stresses. So if I combine both together, it will be like this. So this is my final stress diagram. So this is the final stress diagram. So its amount will be decreased here. And sometimes our tensile stresses become so large that on this tensile stresses may be developed. That I will discuss subsequently. So this is the effect of the direct and combined stresses. So this is what I have explained here. Direct stress is equal to this one. Bending stresses is P upon E in this. So formula will be this. So total stress N in fiber is equal to that plus minus bending stresses. So this is the value of the M, and this is Z. I axis upon Y. I can write it in terms of section modulus or M upon I into Y. Otherwise M upon this I upon Y is equal to M upon Z. So either way I can write it M upon Z or M upon I into Y. The extreme fiber stress is maximum due to bending will be in the top fiber. Obviously it will be, so maximum will be here on this fiber and on this fiber. So maximum stresses will be on this face and this face. So its plan will be like this. So this is the plan of this member. So this is B, this is D. So on this maximum compressive stresses will be there and minimum stress will be there. So this is my maximum stresses, here it will be minimum. And in case of maximum it will be plus, and in minimum it will be minus here. So it will be minus here. This that plus bending will be maximum. So this plus this bending, and it will be that stress minus bending stresses. So that will give the minimum. So this is maximum and this is minimum. So there are three cases. Suppose my bending stress is greater than, my that stress is greater than bending stresses. So in this case my stress diagram will be like this. Since this value is equal to that plus bending here, and this is that minus bending. So when this PO, that stress, is greater than bending stresses, so it will be positive here obviously, and it will be positive here also. Suppose that stress is 25 Newton mm square and bending stress is equal to 15 Newton per mm square. So it will be 25 plus 15, 40 here, and here it will be 25 minus 15, 10 Newton per mm square. So when the direct stress is greater than bending stress, my stress diagram will be like this. Second case is that when both are equal. So if my direct stress is 25 Newton and my bending is also 25. So in this case, my maximum stress here, it will be 25 plus 25, it will be 50 here. And here it will be direct minus bending, it will be 0. So 0 stress will be here. So when both direct and bending stresses are equal together, equal to each other, in this case it will be positive here. It is direct plus bending compressive, and here it is direct minus bending on the tensile face. So my stress here will be 0. What happens when direct stress is lesser than the bending stresses? Suppose my direct stress is this direct stress. This is the direct stress, it is minus 25 Newton per mm square. And my bending stress is like this. This is my direct stress, 25 Newton per mm square. And my bending stress is like this. Suppose this is, it is 30 Newton per mm square. Suppose it is 30 Newton per mm square. On this face it is positive, it is negative here. So it is 25. So these are the stress diagram, direct stress diagram, and this is bending stress diagram. So here it will be, if I add together, so it will be 25 plus 30, it will be 55 here. So 55 Newton per mm square will be the stress here. But here it will be 25 minus 30. So 20 minus 30 will be minus 5. Minus 5 means tensile. My stress will be tensile here. So it will be 5 Newton per mm square. Tensile stresses will be there. So my stress diagram will be like this. So this 5 Newton per mm square will be the stress here. So when that stress becomes lesser than the bending stresses, my stress diagram will be here. So it means on this face there is some sort of tensile stress. So in this case, this is a baseline. My stress here will be above the baseline. So it will be minus here. So in this case, when that stress becomes lesser than the bending stresses, tensile stresses will be developed here. And this is highly undesirable in machinery structure. We do not allow this, because my concrete machinery structure is strong in compression and it is weak in tension. That's why my tendency is to ensure that no tension will be developed on the any face. That's why this is not a desirable situation. So the maximum which can I allow is this one. So this is the perfect situation when no tensile stress is developed anywhere. So this will be my ideal situation, and this is not desirable. So rectangular section, what is middle third rule? Middle third rule is that in many machinery or concrete structures, development of tensile stresses in its section is neither desirable nor permissible, as they are weak in tension. Concrete is weak in tension. For this, for tension to not to develop, my direct stress that should be either greater than the bending stresses or it may be equal to this, so that my stress diagram will be like either this way or this one. So I want my that stress is either greater than bending or equal to the bending stresses. This is not desirable or permissible. So for this that stress to be greater than the bending or equal to this bending, what does it mean? My bending stress is equal to m upon z. It means my direct stress is equal to load upon area. So this is my direct stress, that should be greater than or equal to bending stresses, means this is m upon z and m is load into eccentricity divided by z. So this is here, this direct stress is equal to load upon area greater than this moment m upon z. So this is my eccentricity. So this section modulus I can also write it like this, I upon d by 2. So d by 2 will go here. So it will be like this. So now it will be P into E into d by 2 into I. And this I is equal to, since radius of gyration is equal to root of I upon A, moment of inertia upon area. So K square will be I upon A. So I is basically equal to A into K square. So I can also write AK square in place of moment of inertia I. This 2 will come here. So it will be PE into D upon 2AK square. So now finally, this is my direct stresses. So this. So this and this will cancel each other. Area will cancel each other. It will be 2AK square will come here. 2AK square should be greater than or equal to this ED. Or I can say 2K square upon D is greater than this E. Or I can say E must be less than 2K square upon D. It means for tension not to develop in this section, my eccentricity should be greater than or equal to 2K square upon D. This is the formula, where K is radius of gyration and D is the depth of the member. Suppose this is my, so this is D, this is B. So this is the axis. It will rectangular section. In case of rectangular section, for no tension to develop here, suppose this is my rectangular sections. So in this case, for no tension to develop in the section, the eccentricity must not exceed this one. So this is an important requirement. For a rectangular section shown in the figure, my I is equal to, so suppose this is the section. So moment of inertia here will be, suppose if I am taking moment of inertia about this axis, so it will be B this side into this side cube upon 12. BD cube upon 12 will be the area. About this axis, moment of inertia will be BD cube upon 12. If I want to take moment of inertia about this, it will be y axis, it will become this D into B cube upon 12. So suppose if I am taking along this axis, so this is the case, like this. So this is the case. So for the rectangle section shown in the figure, my moment of inertia will be BD cube upon 12. So upon this, along this axis, it will be BD cube upon 12. This is the value of the I, and here is B and D. So my radius of gyration will be I upon A root. So it will become D square upon 12 root. So K square will be equal to D square upon 12. And what was my condition? Condition was E should be greater than should be less than or equal to 2K square upon D. So E, if I put the value of K square here, it will be 2 into D square upon 12 upon D. So it will be D by 6. Or what I can say, the eccentricity should be equal to or less than D by C for tension not to develop in the sections, or in the maximum it will be equal to D by 6. So this is the value. So this limits value of the eccentricity for no tension to develop in a rectangle sections. However, this eccentricity can be on the other side of the geometrical section. So suppose this is my B, this is D. So for no tension to be developed, the eccentricity value of the eccentricity, it may be equal to D by 6. So you cannot go, this is the central axis origin. So the maximum value it can go from on other side, it will be D by 6 on this side or D by 6 on this side. So this means this total will become D by 3. D by 6 plus D by 6 is equal to D by 3. So this D by 3 is D by, suppose if it is D and is B, so it will be, so this is 1/3 of the total this length. It means my eccentricity should be within this range. So D by 3 means 1/3 of this, and it is in the middle. It is in the middle. So this is symmetrical. This and this are same. So it is, we can say, middle third. This is 1/3 of this, and this is a middle third. So D by 6 from this side and D by 6 on this side. So total will become D by 3. So my eccentricity should be within this middle third for no tension to be developed in the section. So this requirement is commonly known as middle third rule. So in this case, the extreme stresses that can be developed here, suppose here if I am taking this one, so it will be on this section, it will be, this is my B and D. Suppose this is my x-axis, and I am taking, I want to know the stress on this face and on this face. So my z-axis along this axis will be equal to BD square upon 6. So this will be the value of the z, and that stress will be, bending stresses will be equal to M upon Z. Suppose M is PE and ZE will become BD square upon 6. So the value of E here will be, since it is D by 6, so if I can put this value here, it will be, so my bending stress is equal to PE upon Z. This is M upon Z. the value of E is equal to D by 6. So that can be D by 6. This and this. This is D by 6 and this is D by 6. So the value of E, if I can put here, and Z is equal to BD square by 6. So this 6 and 6 will cancel each other, and this upon BD. So if I put this value here in place of Z here, so this is direct stress and this is M upon Z, bending stresses. So maximum stresses will be this one. So this is direct stresses will be load upon area. So this is my B and this is D. So this is B, this is D. So direct stress will be load upon area, which is P upon BD. This is my direct stress, and my bending stresses will be, suppose this load is acting here and there is a eccentricity, so it will bend like this. So compressive stress will be developed here. So my bending stresses will be plus here, it will be M upon Z. So M is equal to P upon E, P into E upon Z will be moment section modulus about this axis. So it will be BD square by 6. So it will become 6 P upon BD square. So this is basically P upon BD is common here. So I can take P upon BD common here. So this 1 plus minus this. So this will be the maximum stress here on this face. So maximum value will be that plus this one. And here the maximum stress for no tension to develop, that will be 0. So this was the case. So this was the case. So if I put this value here 0, it will be, if I put this value 0, it will give E is equal to, then it will be 1 minus 6 E upon D. It will be E is equal to D upon 6. That's what I have explained earlier. So my eccentricity should be within this range, D by 6 on this side or D by 6 on this side. So it should be within the middle third. So it is called a middle third rule. In case of circular section, so my condition is that E is less than or equal to 2k square upon D. So this is the my formula for no tension to develop here. So here the value of I for circular section, moment of inertia I upon A root is equal to K. So K will be equal to moment of inertia is pi D4 upon 64 divided by area. So it will be D square upon 16. So my value of root of this is equal to K. So K square will be equal to D square upon 16. So if I put this value here, so it will be E 2, in place of K square it will be D square upon 16 divided by this D. So this D becomes D here. So it will be D by 8. So D by 8. If this die is small 8, it will be D by 8. So the maximum eccentricity in this case for no tension to develop here, it will be d by 8. So d by 8 on this side from the origin and d by 8 on this side. So d by 8 plus d by 8. So it will become d by 4. And in this case also it will be d by 4, d by 8 and d by 8. So it will become like this. So this portion is d by 4. So we can say it is a middle fourth. This total is d and it is the midway. So we also call it as a middle fourth rule. So for no tension to develop here, my maximum eccentricity can be d by 8. Thus, in order that tension is not to develop, the load line must fall within the middle fourth of the section. So d by 8 plus d by 8 will become d by 4. So d by 8 here in d by 8 on this side and d by 8 on this side, total will become d by 4. In case of hollow section also, my moment of inertia is equal to pi upon 64 outside diaph. So this is d and this is small d. So my moment of inertia will be this one, area will be this one. So k is equal to I upon a, radius of gyration is equal to I upon a, so k square is equal to I upon a. So it will be this one, d square plus d square upon 16. So for no tension to develop here, my E should be less than or equal to this. So if I put the value of k square here, it will become 2 d square plus d square upon 16 divided by this d. So it will become this one, d square plus d square upon 8d. So the maximum eccentricity can be d square plus d square plus 8d. So this is in case of circular sections, hollow circular. Core of a section. What is the core of a section? Core or kernel. If the line of action of the force is on the either of the axis of the sections, the bending is unsymmetrical. Suppose this is my section, this is x-axis, this is y-axis. Suppose my load is acting here. So this is not on either of the x-axis. It is neither on the x-axis nor on the y-axis. It is acting here. So in this case, my bending will be unsymmetrical. It will create compression here. Because of this, it will deflect like this. So this load is acting here. Because of this load, it will like this. It will be compressive here and tensile here. So if I consider about effect of this, but effect of this along this axis, it will be opposite. So it will be like this. So this is my section vertically. If I see, so it will along this axis, so it will bend like this. So there will be compressive. So suppose this is my beam, and because of this load along this y axis it will be like this, and along this axis there will be compression and tension here. On this face there will be compression, this will be tension. So it will So this is the case. So it will bend like this. So if the line of action of the force is not passing off any of the axis, in this case the bending is unsymmetrical. So if the stress is not to become tensile, the line of action of the force must be cut the cross section within a certain area. This area is known as the core or kernel of the section. The shape of the core or kernel of a sections depends upon the shape of the sections. Like this, what I have discussed here, my eccentricity should be within the, for no tension to be developed, it should be within, suppose this is my B and this is D. So it will be B by 6, it will be B by 6 here. So another on either side it can go, that is B by 6 or B by 6 here. And if on this axis, if it is D, it will be D by 6 and it will be D by 6. So my loading should be within this. If I meet all these points, so it will become a rhombus. It will become a rhombus. So we can say this is a rhombus and we call it as a core or kernel of a sections. So when my load, suppose my loading is within this much area, then no tension will be developed here. If my line of action of the P will go outside of this area, then tension will be there at some other point on the sections. For the condition that no tension to be developed, my loading should be within this one. So other way it will be B by 6, B by 6, it will be D by 6 and D by 6. So when I meet all these points, it will become a rhombus. We call it as a core or kernel of the section, and it depends upon the shape of the section. So in case of rectangular sections, it will be like this. And so this is what I have explained here. So this is the P point here. So it is a rhombus. If it is a B, then the maximum it can go here, B by 6 and B by 6 here. So total will be B by 3. In this side D by 6, D by 6. So it will be D by 3. This is the middle third here. So this is my shape. So my moment of inertia about this x-axis will be, this is D and this is B. So about this axis it will be dB cube upon 12, and about this y-axis it will be BD cube upon 12. So my moment of this is bending moment about this x-axis will be this load P. Suppose this is the point where the load is acting. So its position is there. Suppose if this is the origin, this is x-axis, this is y-axis, and the load is acting here. So its ordinate along this x-axis is, suppose this is x, and along this y-axis it is y. So its coordinate are p, x and y. Coordinate is x and y. So this is the x and this is p. So its bend moment, it will create a bending moment along this axis. It will be this load into this perpendicular distance. So p into this y. So this will be the moment about this axis, and along this y axis it will be this load upon this perpendicular distance. So it will be p into x. So stresses at any point having coordinate x bar, y bar, x dash, y dash will be given by this formula. So one is due to direct stress, it will be load upon area, and due to bending it will be mx upon ix into y dash plus my upon y into x bar. So this will be the formula. Suppose that there is any point where we want to know the stresses. Suppose suppose I want to know my stress about this point. So it will be, total stress will be 1 because of direct load, that will be load upon area, simply it will be compressive throughout, plus because of this load there is a moment MYY. So moment about this will be P into X about this, and it will create, here it will act like this. So it will be like this. So it will create compression here and tensile here. So my bending stress will be minus here on this face, and value of M will be P into this X divided by the this IXS, this will be IYY into the point where we want to know the stress. So if its distance from this point, from this origin is d by 2, then it will be d by, suppose if it is x bar, so it will be x bar, and because of this so its effect because of this is this one, and also because of on this face, along this face, it will create, my moment will be, so along, if along the x-axis face, my moment will be P into this y. So P into y will be the moment, and it will create, if I will see along the, on this face, it will create compression here, tensile here. So it will be minus here again. Moment will be P into this one's distance y divided by moment of inertia about this section. So this will be xx into its distance from this origin. Suppose this distance is y dash, so it will be y dash. So this will be the formula by which I can find the stress at any point on the section. So if my point is, suppose it is in coordinate 1, so if it is here, so if I take this point, so it will be compressive throughout, due to light load it will be compressive, and because of this also it will be compressive, and because of this along this it will also be, so in this first coordinate it will be throughout positive. So its value will be like this, corresponding moment of inertia, and this, so it will be, if I take B upon D and 12 common, so it will be 1 upon 12 plus y dash upon this B square plus this one. At any point D, suppose x is equal to minus d by 2 and minus b by 2, means here at this point. So it will be minus here, both in both the cases the fourth coordinate, third coordinate, in the third coordinate. So here my, suppose if I take any point here, suppose this is my x bar and this is y dash. So here my, this is on the negative side of the origin, on this side it is positive, it's a negative, on the upper side it is positive, it is negative. Suppose if my point is like this, where value of x dash and y dash both are negative, so then it will be tensile here, because of along this axis, if I consider this moment, it will create compression here, it will be tensile. If I consider along this action, it will be compressive here and it will be tensile here. So the moment along both the axes will create a tensile stresses here. So it will be minus here because of both. So it will be like this, and if P minimum reaches a zero value, for no tension to develop here, the maximum that can be, this will be 0. So when the effect of bending will become so large, then it is equal to the that stresses, then maximum it can be 0. When this becomes 0, then it will become 1 upon 6 is equal to y upon b plus x upon d. So multiplied 6 both side, it will become 6x upon d plus 6y upon d is equal to 1. And this is the equation of a straight line whose intercept on the x-axis and y-axis are respectively b by 6 and d by 6. So this is the equation of a straight line, and on the x-axis, suppose if I put y is equal to 0 here, it will give x is equal to d by 6, and suppose if on this axis I put x is equal to 0, then y will be b by 6. It means, so this is d by 6, this is also d by 6, this is b by 6, this is b by 6. So if I connect all these points, 4 points, it will become a rhombus. So this is true for the load line, the first quadrant. Similar limits will be applied in the other quadrants. The stress will be wholly compressive throughout the section if the line of action of the P falls within rhombus, the diagonal of which are a length of b by 3 and d by 3. So its dimension will be obviously, it will be d by 3 total, and it will be b by 3. When I sum both, it will be d by 6 plus d by 6 d by 3 and b by 6 plus b by 6 b by 3. So this is called a rhombus or core or kernel of the section. For solid circular sections, this becomes this one. It will be d by 8 and d by 8 on both sides. So d by 8 here, d by 8 here. So it will be d by 4 on other side. So this is called core or kernel of the section for circular section. So its diameter is d by 4. For hollow circular section, it will be this one. So the maximum this can be 8d d square, d square plus d square upon 8d plus this one. So when multiplied by 2, it will be the dia of the this core. This is the core or kernel of the section. For I section, it will be like this. So this is the core of a I section. The core of it is built rhombus. So let's take a example. A beam of carries a UDL of 50 kN over its span of 2 meter along with the axial compressive force of 50 kN. So this is my beam. Its span is 2 meter and UDL of a weight 50 kN per meter is acting here. And along with this 50 kN, this direct force is also acting here. So the beam section is rectangular having depth equal to 240 and width is 120. So this is the section, this width is 120 and this depth is 240. I have to find out the maximum fiber stress. Number 1, maximum fiber stress will be obviously here. So 1 is due to direct stress, this will be P upon A, and due to bending it will be like this, compressive and tensile. So this is P bending compression, bending tensile, and this plus this will be the final stress like this. Compressive may be tensile, that will be C. So this plus this. So he wants to know the maximum fiber stress is here. Secondly, the fiber stress at a point 0.5 meter from the left end of the beam and 80 mm below the neutral axis, means 0.5 meter from this spot. So here you want to know the maximum fiber stresses and 80 mm here below the neutral axis. So this is my neutral axis. So 80 mm below means on this layer. So in this layer means here in this layer 80 mm below the neutral axis. So this stress will be this stress plus this stress, which is at this layer, at the layer of air. So this is my B. So let's start. So it is very simple. First of all, we will compute the maximum fiber stresses. So this beam will deflect like this. So this will be bending because of this. So its Z will be BD square upon 6, 120 into 240 square by 6. So this is my section modulus. Its area is 120 into 240 is this one. And moment of inertia is equal to about this x BD cube upon 12. So this will be this one. So maximum fiber stresses will be obviously maximum, where the bending moment is maximum. Its bending moment will be like this, WL square by 8 is maximum here at the mid span. So I will take the moment at mid span. So it will be WL square by 8. So 50 into 2 square upon 8. This will be my maximum bending moment. It is 25 kilonewton meter. Bending stresses will be M upon Z. So value of M is 25 kilonewton per meter. So it will be Newton mm. So M upon Z. Z is the section modulus. So section modulus Z is equal to this much. This divided by this one. So I will get the maximum stress. So this will be, so my stress will be like this. Suppose this is my section. So it will be like this. About the neutral axis, it will be top 21.701 in the bottom also. So this is positive, this is negative. So bending stress is equal to M upon Z on the top fiber, and my direct stress obviously will be equal to load upon area. So it is equal to load upon area. This direct load is also creating a direct stresses throughout. So throughout it will be compressive. So this stress diagram will be like this. So due to direct load, my stress diagram will be throughout compressive. It will be like this. This is direct stress, load upon area. It will be throughout compressive. So this is due to bending. And the value will be direct load upon area. It is 1.736 Newton per mm square. So maximum fiber stresses obviously will be here on the top. This is positive, this is positive. So maximum here. So this plus this will be, this will plus this will become. So when I add both these stresses together, it will become, this will be 21.70 plus this is 1.736. So it will be this plus this will be 23.43 Newton per mm square. So it will be positive, and on the bottom it will be this minus this. Since it is it is compressive 1.376, it is compressive, and it is minus 20. So it will be tensile. So the value will become, it will be 19.965 in the bottom. So it will be 19.965. It is tensile, it is compressive. So maximum compressive stress will be here, this one. So this is the answer. So this is my final stress, this is direct stress, and this is bending, and final is, so this is due to bending, this is due to direct, and finally this plus this will become this one. So secondly, he wants to know the fiber stress at the given locations. So given location is at this point. So this is the point which is 0.5 meter from this point, A spot. So at this point he wants to know the stress. So first I will calculate my moment at these sections. It will be, so obviously my total load is 50 into 2, it is 100 kilonewton. So reaction here will be 50 kilonewton and 50 kilonewton both. So here moment will be 50 into this much distance, it will be sagging, so positive, minus this will be, because of this it will be WL square by 8. So this I will get moment here, so this will be my M here. So my bending moment at this point is 18.75 kilonewton meter. When I convert it in Newton mm, I will multiply it by 10 raised to the power 6. So bending stress will be M upon I into Y. This is my formula. F upon Y is equal to M upon I. So F is equal to M upon I into Y. This Y is the distance from the neutral axis at which we want to know the stress. Suppose this is my B, this is D, this is the neutral axis, and my stress diagram will be like this. So at any point, suppose I want to know stress at this level, which is 80 mm below the neutral axis at this layer, so it will be M upon I into this distance. So my moment is this much upon my moment of inertia is, this is the moment of inertia, M upon I into this much distance. So that's will give this value 10.85 Newton per mm square, and this is tensile here. So it is 10.85 Newton per mm square. So it is tensile in the same. So it is minus. And stress, because and this is also a direct stress. Direct stress is equal to P upon A. My P upon A is the direct stress, and that was equal to 1.736 Newton per mm square. Load upon area. This one, this is the direct stress due to this load, 50 kilonewton divided by area, and this will be constant throughout. So at this layer also it will be 1.736 corresponding at this layer. So my final stress at this layer will be, on the top it will be, obviously at this layer I am interested only at this layer, so it will be minus 10.85 plus, this is plus, so it will be finally minus 9.115 Newton mm square. I will get the stress at this layer. This is the answer. Second example, a masonry structure of 2 meter into 3 meter supports a vertical load of 50 kilonewton as shown in figure. Find the stresses developed in the corner of the pier. So this is the masonry structure. So this is the 3 meter length, its width. This is the depth is 2 meter. So my load is acting at this point, which is, and this is the origin. This is my x-axis, this is y-axis, this is the origin, and the location of this point is such that this distance is along the x-axis. Its distance from this y-axis is 0.8 meter, and its distance from this x-axis, when I measure it along the y-axis, it is EY. Suppose eccentricity along the y-axis it is 0.4 meter, it is 0.8 meter. So this is the location of the load. So I have to find the stresses developed at the corners of the pier. So there are 4 corners. One is this one, this one, this one, and this one. I have to calculate the stresses at all the 4 corners. Secondly, what additional load should be placed at the center of the pier show that there is no tension anywhere in the pier sections. So what additional stress I have to place at the center of the pier, show that there is no tension anywhere. Suppose in the first case there is tension at any of the corner. So if I want my tension to be 0, then how much additional load is required to be placed? Third, what are the stresses at the corner with this additional load? So with this additional load, what will be my final stresses? So there are 3 things. So let's focus on the first one. So this is the section. So its area is 2 into 3 meter, 6 meter square. Its area will be 2 into 3, 6 meter square. And its moment of inertia about this I-axis, means about this is my I-axis. So about this moment of inertia, it will be this 3 into 2 cube divided by 12. So this will be about this axis. It will be 3 2 cube upon 12. So I will say I-axis is equal to this much, 3 into 2 cube upon 12, and about this axis it will be this side 2 into cube of this side divided by 12. It will give I by y. So this is the value of the I by I, 4.5. Eccentricity about the x-axis. So this is my x-axis. So about this, its eccentricity is 0.4 meter. This is my EY. Eccentricity about y-axis. So about this, it is 0.8 meter. So it is EX. So my moment about this x-axis will be about this x-axis. My bending moment will be load into eccentricity. So about this axis, my mx bending moment about this axis will be this load into the perpendicular distance from this axis. This is x-axis, this is the perpendicular distance. So my mx will be this load into this. This is EY. So this will be my mx. And about this y-axis, my bending moment will be this load into this much perpendicular distance from this y-axis. It will be P into EX. So this is this one and this is this one. Now distance of A and B from the y-axis. Suppose this is my A point. So its distance from this axis, this distance we call it as YA. This is YA, and its distance from this distance which is along the y-axis, it is XA. This is the origin, this is YA, this is XA. The distance of this point from this origin is along the x-axis, it is XA, and this is YA. So distance of this and this point also, so it will be XA and YA. So here it will be IA, this will be positive and this will be negative. So it is XA here is positive, it is on this coordinate, and YA will be, YB will be, this is XB, XB will be this one, and YB will be this one. Both are positive since it is in the first coordinate. So this is the distance of A and B from the y-axis. So distance of A and B from the y-axis is equal to this, and both are half of this. So it will be 1.5 meter, 1.5 meter. And distance of A and D from the x-axis. Distance of E and D from the x-axis. So this is the A point. So from this x-axis, this is the distance, it will be YA, this will be YD. This is the x-axis. So let's start. Stress at the corner A means this, if I so this is my P point, this is x-axis, this is y-axis, this is A, this is B, this is C, and this is D. So it was Ex is equal to .8 meter. This, and this is Ey, it is 0.4 meter. So suppose I am taking this corner. So stress at this corner will be because of three component. One will be that stress that will be load upon area. So suppose if this is the structure, this is the load. So this load is acting here. So my direct stress will be load upon area simply. So this is P upon A. So my P is 50 kilonewton divided by this area 2 into 3. So that will give P upon A. So this will be throughout compressive. This will be throughout compressive. So it will be 50 upon 6. 50 is the load and it is 3 meter and it is 2 meter this length. So area will be 2 into 3. So this will be throughout compressive. Plus this, its moment about this axis P into 0.4, this load into this distance P into this Ey. P into Ey is equal to mx. Its moment about this x-axis is equal to this load into this perpendicular distance. So my mx axis is equal to, this is the load which is equal to 50 kilonewton into this Ey. So my mx is equal to, so it will be mx axis upon I x axis into this much distance. Suppose if I am taking along about this axis, so it will be this distance. It is YA. This is YD. So this is XA. This is XA. This is YA from this origin. So I am taking these points. So this, because of this load, there is a moment mx axis. So mx axis divided by I axis into this distance YA, that will give the stress here. So because of this load, this is the load into this distance mx axis about divided by I axis into this distance. This is the distance from the neutral axis, and this distance, it will give stress here because of this. So the moment of this load, because about this axis, it will be this load into this distance. This is 50 kilonewton into this one, it will be 20 kilonewton. So my m-axis is equal to 20 kilonewton meter. This one. So this load into this distance is 20 kilonewton divided by IY. So this will be my moment of inertia. So moment of inertia is I-axis, this is 2. So this divided by 2 into its distance from this distance. This is 1 meter. So total is 2 meters. So it is 1 meter and 1 meter divided by 2. So this will give stress because of, so about this axis, the effect of this load will be, it will create compressive here and tensile here. The effect is like this. So if this is so its effect will be, so there will be compressive here and here, it will be compressive, and it will create tensile and tensile on this corner. So it will bend like this. It will bend like this. So about this axis, it will bend like this. It will bend like this. So compressive stress will be developed here and tensile will be on this corner because of this load. So this will create compressive here and tensile will be at this point. If I want to draw the deflected shape about this axis, it will be like this. About this axis, x-axis, it will be like this. No, not able to. So and both the points, at this point and this point, there will be a compressive. So at this point, it will be compressive here. So the compressive is positive. And the effect of this load about this y-axis, it will be negative here. Since it will create, so this load into this distance, this is 0.8 meters, so it will be 40 kilonewton. This will be my MYY, 40 kilonewton. This is 40 kilonewton meter divided by its moment of inertia about this IYY. It is equal to 4.5. So this 40 divided by 4.5 into this one distance, this distance. So this is XA, 1.5 meter. So about this axis, this moment will create compression here on this face. It will create compression on this face. On this face, it will create compression, and tensile it will create here. So its effect will be minus. So my final stresses will be 8.33. This will be plus 10 minus 3. So it will be 5 kilonewton per meter square is the stress at this corner. And at corner B, at this corner, about this axis it will be MYY. About this axis it will be MXX. and its moment of inertia Ixx, and here it will be Iyy, and this distance is xa, this is ya. Now let's go on this point B. So one is direct stresses, which is load upon area, that will be constant, plus about this axis mx axis moment, mx about this axis its moment will be, this is 50 kilonewton, so 50 into 2.4, this is mx axis about this I axis into this distance, this is yb, that will give stress here, and this will create about this axis. If you see the effect of this load, so it will be compressive here, it will create, this load will create compression on this face, and tensile on this face, so it will be compressive here, means positive. And if I see along this y axis, it will create compression in this face, on this face it will create compression, and tensile will be there, so here also it will be compressive, so it will be 40 myi upon Ii into this distance, so this will be positive. So in the first coordinate itself also all the value are positive, it will be throughout compressive, so the value will become this one. If I want to know the stress at corner C, at this corner, so at this corner, so load upon area, this will be the same, so it will be myy, this moment about this axis, it will be load into this distance, so it will be myy upon moment of inertia Iyy into this distance, this will be y into xc, this will be xc, from this origin it will be xc. And about if we see along this y axis, the load effect of this load, on this side it will create compression, and on this face it will create tensile, so it will be minus here. No, about myy stress at this corner, myy upon Ia into xc, is the stress at this corner, it will be about this y axis, so about this it will be myi upon yii into this distance, this is xc, so it will create compression here and tensile on this half portion, so it must be minus. So the value of myy, it is 3 meter, it is 2 meter, and it is, so it will be xc is this one, so this load will cc Vc along this axis, it will create yy upon yy into, I think I think this is D, this is C, so C will be this one, so C will be, this is D, this is not C, C is this one, yes. So at this point, because of this load, compression will be on this right portion. On this much portion there will be a compression. So obviously compression will be there. So this load into this distance, this is the moment divided by the moment of inertia about the y-axis into this distance from the neutral axis. It will be compressive here, and because of this, if I see this x-axis, so it will create compression on the upper half and tensile on the lower half. So its effect will be minus. So after putting the corresponding value, I will get this one. And stress at corner D, at this corner which I was calculating here. So here, if I see along this x-axis, it will create compression here, it will be tensile. Along this x-axis also, about this axis, it will create compression here and tensile here. So effect of the moment about both the axes, it will be minus here. So it will be minus 15 kilonewton per meter square tensile. So effect of this load, if I see along the y-axis, it will create compression here and tensile on this face. So this is the load. So it will bend like this. So here it will be compressive and it will be tensile here. If I see along this axis, about this axis, it will create compression here and tensile here. So about this axis, if I see, it will bend like this. Oh no. If I this effect of this, it will be like this. About this axis, there will be compression here and tensile will be here. So at this corner, it will be minus 15 kilonewton per mm. So these are my corner stresses. So what he wants to know that additional load, how much additional load at the center I have to apply for no tension to anywhere. So here stress in my all the corner are positive. At A it is 5 positive, and B it is this one 31.66. At C it is 11.66. So all are compressive, positive. Only at D it is tensile, minus 15. So what he want to say that if I want my tensile stresses to be 0, if I want no tensile stresses to be developed anywhere, for that how much additional load I have to apply here. So that additional load will be applied at the center. Means this is the second condition. What additional load should be placed at the center of the pier so that there is no tensile stresses anywhere in the pier sections. So obviously, if you apply a load here, that load, suppose delta is the load divided by this area. So the effect of this should be plus. So how much? My stress at this point is minus 15 kilonewton per meter square. If I want my this tensile stresses to be 0, then for this I have to place so for this to become this stress to be 0 at this, I have to place plus 15 kilonewton. My load should be such that my load, this W at this origin should be such that it will create plus 15 kilonewton per meter square stress here, so that it will become 0. And since it is acting at the center, so if my W is like that it creates a compressive stress of 15 kilonewton per meter square at this corner, then it will be 0. Since it is minus 15 kilonewton per meter square, so my load should be such that it will create 0. And it is acting at the center, so it will create plus 15 and plus 15 at all the corner. So here it will be 0. So how much additional load? It means W upon A should be equal to 15, and W is equal to 15 into this area. Area is 2 into 3. means 90 kilonewton load I have to apply additionally at the center of this sphere, so that my stress at all the corners are throughout compressive, no tension. So this stress will become 0, and there will be further addition of 15 kilonewton at all the other corner. So this much amount of additional load. So additional stress at all corner means there will be a increase of 15 kilonewton per meter square at all the corners. So previous stress is 5 plus 15, this plus 15, this plus 15 will be there, and D obviously it will be 0. So this is the question. Next question is, a short hollow cylinder cast iron column having outside dia is 400 and inside dia is 300 was cast in a factory. So this is my section of a cylindrical column. This is the column. Its outside dia is 400. So this dia is outside dia is 400 mm, and its internal dia, this dia is, the dia of this one is 300 mm, this one. On inspection, it was found that the base is eccentric in such a way that the thickness varies 30 mm at one end to 70 mm at the other end. So its thickness is 30 mm here, and it is 70 mm here. So its thickness is like that. So this is my bore. So it is not concentric, it is eccentric. Its thickness is 30, it is 70 here. Calculate the extreme intensity of stress induced in the section. If the column carries a load of 2000 kilonewton along the axis of the base, so I have to find out the along the axis of the base. So my load is acting here. Axis of the base means this is my bore. So my bore is, this inside bore is, its center is this one. This is the internal bore, and its center is this one. So this is the center of this internal bore. So it is 150 mm. Obviously it is 150 mm. So this will also be 150 mm. So this is 150 mm, and this is the center of the whole column. So it will be 200 and 200 on both the sides. So this is the center of the bore where the load is acting. So my load is acting at this point. So this is the position where the load is acting. So it is acting at the bore axis. My bore axis is this center of the bore. So my load is acting here. So first I have to find out its area. That area will be, net area will be outside area minus internal area. So obviously it will be, my net area will be outside area pi by 4, 400 square minus 300 square. This I will get the net area. It is equal to this much. So this is my area. And if I want to know the distance of the centroid of the section from A, so for this, suppose this is the centroid, I want to know its position. So its position from this axis, this is the x bar. For this, what I will do, my x bar will be area of the hole, it will be pi by 4 into 400 square into its distance from here. So the outside area of the whole dia, its center is here. So this C is the center of the this outer circle 400. It means it is 200 from here. So its distance from this point to this A is 200 minus area of the inside bore pi by 4 into 300 square, and its distance, so its origin, this is the center of the bore, so this distance into this distance, it will be since it is 150, it is 180, so total is 400 minus this 180, I will get 220 divided by this area. So with this I will get x bar. My x bar will be this one, 174.29 mm. So this is so my x bar is so I got the position of the centroid. So this G, the distance of the centroid from this A point is this much, x bar, it is 174.29 mm. This is the centroid of the net area, it's where this is the position, so its position from this is 174.29. so if I want to know the moment of inertia about this centroidal axis, so there will be two axes, one is x axis, another is y axis. This is my y axis, this is x axis. So I have to know the stresses about, so my extreme stresses will be here. Since about x axis this is symmetrical, about this x axis my section is symmetrical, upper half is equal to the lower half, but about this y axis it is not symmetrical. So obviously due to unsymmetrical there will be eccentricity, and due to eccentricity additional stresses will be developed, additional compressive, additional tensile. So I will not consider my moment of inertia about this x axis, I will consider about this y axis only, because my bending will be about this axis only. About x axis no bending will be there, it is symmetrical. So its moment of inertia about this y axis, that I will calculate. So my eccentricity obviously will be, this is 174.29. So my load is acting at this point. So the position of this load plus from this to this is the eccentricity. So this is 174.29 meter obviously, and this is 180 from here, and it is total is 400. So obviously it will be 220. So this distance from this point to this 220 minus this 174.29 will be this much. This will come 45.71 mm. So this is the position of the load where my load is acting, and this is the centroid. So this much is the eccentricity. So moment is equal to load into eccentricity. So my load is 2000 kilonewton. So 2000, my moment will be P into E. So 2000 kilonewton raised to the power 3, it will be Newton into this eccentricity 45.71. So this will create a moment. So on this face it will create compression, on this face from this centroidal axis it will be compressive, it will be tensile here. So what I have to know, I have to find the maximum stresses, extreme intensity of stresses. For this I want to know the moment of inertia about this y axis. So Iyy is required to be find out. So it is required to be known. So first I have to know its moment of inertia. So its moment of inertia will be this much. So this is my moment of inertia. So its moment of inertia will be, first of all, moment of inertia of the hole, it will be pi into 400 raised to the power 4 upon 64 plus its area. This is the moment of inertia about its this is the center of the whole circle. So about of moment of inertia about this plus its area pi by 4 into 400 square. This is the area into this much distance. Its out center plus this g. So this distance will be obviously equal to 25.71, as this distance is, this is 200, this is 174. So this distance, this is the center of the outside circle. So this is 200 minus this 174.29. So it will be 200 minus 174.29 square. So with this I will get the moment of inertia of the hole, and I have to subtract the moment of inertia of the bore also. For this I will put minus here. So for the bore, the moment of inertia will be pi up into its dia is 300 plus its area into its distance from the g. So this is equal to 45.71 square. So with this moment of inertia of the outside minus moment of inertia of the inside bore, I will get this I. Its value will be 794.40 into 10 raised to the power 6 mm 4, and moment is equal to obviously this load into this eccentricity. So 2000 kilonewton into this E, I will get this M. So this is my moment in Newton per mm. So my bending stresses will be, so this will be my bending tensile, this will be compressive. So my moment, which is equal to P into E divided by this IYY into its distance. My G is here, so my neutral axis will be here. So this distance is 174.29. So obviously here it will be compressive, it will be negative here. So moment M upon IYY into this 174.29, this will give my bending tensile stresses, and this will be obviously here. So this will be 20.06 Newton per mm square. Oh, it will be tensile here, and on this end it will be compressive. So it will be bending compression stress. So obviously its stress diagram will be like this. So this is the neutral axis. So this distance is from the centroid 174.29, this much distance. So this is tensile, and its value is equal to 20.06. So my stress, this stress is 20.06 Newton per mm square, and I want to know the stress here. So at this end it is compressive. So this distance is obviously equal to, total is 400 minus this, so it will be 400 minus 174.29, this one, and this I have to know. So this side divided by this distance, both are similar triangle, is equal to this side divided by this side. So this will be equal to 20.06 divided by 174.29 into this much, 400 minus 174.29. So this I will get 25.97 Newton per mm square. So this is the bending compression. So my bending compression is 25.97. So this is 25.97. So this is one part. This is bending compression. Obviously my maximum stresses will be here on this face, because my direct load is creating compression everywhere. So this plus my PO, direct stress, is equal to load upon area, and my this load is 2000 kilonewton is acting at this divided by the area. So this is acting here at this O point. So this will create a direct stresses. So it will be 2000, this is Newton upon area. So this direct stress is equal to, my area is this one. So this value is 36.38, and this is compressive also. So this value is, because of this stress is 36.38. This is also compressive, this is also compressive. This is load upon area. So this is bending compression, this is direct compressive. So when I put together, this will become this much. So this will be 62.35 Newton per mm square. This is my bending compression, and this is due to direct stresses. So total is, this is compressive. So obviously it will be here, and on this face it will be direct minus bending. So obviously this is 20, this is minus tensile. If I want to know my stress at this end, it will be, this is tensile, bending tensile, and this is compressive. So this is 36.38. So I will get 16.38. So this will also be, finally my final stress diagram will be like this. When I combine both together, so my final stress diagram will be like this. So it will be (62.35), 62.35, both are compressive, and here it is, here also it is 16.38. So this will be my final stress diagram. It is compressive here also, because that stress is more than the bending tensile. So this will be my final stress diagram, and this is my answer. So maximum compressive stress will be here, and this will be 62.35. So the extreme intensity of stress induced in the section is this much. So this is the end of the section. I hope you enjoyed my lecture. So thank you very much, and have a good night. Thanks.